Okay, this video is going to be chapter 13 from the book Medical Reformation and Vegan Renaissance. We're going to be talking about diabetes. I'll have to split, it's a long chapter, so I'll have to split it like into chapter 13A, B, and C. Okay, so here we'll get started. And what I'm showing you here is what I would call a staging system for diabetes. And I sort of made this up myself based on a lot of reading, but it's also sort of associated with a lot of the ideas that have come out of diabetes experts like Gerald Shulman and Roy Taylor. Gerald Shulman won the Banting Award as the best diabetes researcher in the world in 2018. And you can watch his lecture. It's available for free on YouTube. Okay, and the other guy, Roy Taylor, he won the Banting Award, Best Diabetes Researcher in the World 2012, and he has lectures available for free on diabetes. They're very good. Both of them are excellent. And they worked together for a while at Yale. Shulman's sort of based at Yale. He was sort of a Harvard MGH guy, Mass General Hospital guy, and then he did this work with nuclear magnetic resonance spectroscopy, okay? And he was looking at skeletal muscle, and what they found was the earliest detectable finding of insulin resistance is the accumulation of fat in the skeletal muscle, okay? And then Roy Taylor went back to England, and he did some pretty big papers on the topic of fatty liver. And what he basically showed was if he could get his patients to lose 30 or more pounds of weight, they would lose the weight, the fat initially, especially from the liver. It's sort of the metabolic workhorse of the body, and things happen fast in the liver. But once they lost 30 pounds of body weight or more, the liver, fatty liver would often go away, and subsequently so would their diabetes. He actually was routinely able to cure people who had diabetes 4 years or less if they lost that 30 pounds. Okay, so that's pretty interesting. Basically, when you've got fat accumulating in the skeletal muscle, you'll have a tendency towards postprandial. Prandial means eating, so postprandial, after eating, hyperglycemia, high blood glucose. When you start accumulating a worsening fatty liver, the liver regulates blood glucose level during the fasting phase. So that's most of the time. And, for example, while you're asleep at night, and once it becomes fatty, it starts losing the ability to regulate blood glucose level. It'll have a tendency to keep pushing too much glucose out into the blood. It's not able to accurately sense the blood glucose level. And so the person will stay persistently hyperglycemic. So that's fasting hyperglycemia, as opposed to postprandial hyperglycemia, after eating hyperglycemia, when you just have the fat accumulation in the muscle. And they'll call that intramyocellular lipid accumulation. So intra, inside, myo, muscle, myocellular, muscle cell, lipid. Lipid is just another word for fat. So anyways, the point of all this is fat is the guide to how you stage diabetes. Fat accumulation in the skeletal muscle is like the first stage. Fat accumulation in the liver is sort of the second stage. And progressively, fat will then continue to accumulate in the pancreas. If you talk to any radiologist, ask them, do you ever see fatty atrophy of the pancreas? They'll say, yeah, they see it all the time. Most of them won't be aware, though, that that's an indicator of type 2 diabetes. Okay? And once you get, this chronic hyperglycemia, postprandial and fasting hyperglycemia, the high glucose in the blood starts to damage parts of the body. It'll damage the eyes, that's diabetic retinopathy. It'll damage the kidneys, that's diabetic nephropathy. It's also damaging to the small blood vessels, let's say in the foot. They call it a diabetic small vessels, microvasculopathy. Okay. Fat accumulation in the beta cells of the pancreas, they're the ones that make the insulin, will lead them to lose their ability to make insulin. And once the person can't make insulin anymore, then they become insulin dependent. So you can think of it, diabetes. I'll give you what are sometimes considered the four types of diabetes. Type 1 diabetes typically is a very young person, autoimmune form of diabetes, most commonly associated with milk, dairy products. Type 2 diabetes is the most common type of diabetes by far, over 90% of diabetes, and that's your typical middle-aged and older person who's fat. Nowadays, there's so many fat young people that we're seeing type 2 diabetes, and even teenagers and 20-somethings, okay? Type 3 diabetes is sort of a not as strongly entrenched term, and that relates to dementia in association with diabetes. And in my dementia lectures, I'll explain why having insulin resistance is associated with cognitive decline. That's a little bit of an involved topic, and it goes with all this other brain stuff, so we'll get to that in the brain lectures. Okay, then I know I said there were 4 types. The 4th type that I haven't mentioned yet is type 1.5. And type 1.5 has a combination of features that are similar to type 1, autoimmune-induced diabetes, and type 2. And it's also sort of a late onset type 1 in some ways. Okay, those 2 guys over at Mastering Diabetes, I think they're pretty good. That's like Bobby Bittero and Cyrus Kumbada, and I think they call themselves type 1s. They almost sound to me a little bit like type 1.5-ish in the sense, but they would know better. They would know themselves better than I would know them, in the sense that their diabetes came on older. I think they were teens when it sort of came on for them. Okay, and then what happens is insulin resistance initially is primarily due to elevated dietary fat, but the skeletal muscle cells, I'll explain how that works, how the dietary fat, especially SAT fat, causes insulin resistance. However, these other cells in the body, like the eye and the retina, in the kidney, and the endothelial cells in the small arteries, for example, these cells have what's called constitutive uptake of glucose. What that means is glucose just enters these cells in proportion to its concentration in the blood, and they can't control it. Therefore, if there's persistent hyperglycemia around the clock, postprandial hyperglycemia, fasting hyperglycemia, these cells end up taking in too much glucose because they can't control it. And what that leads to is something we'll call overnutrition, and it starts to damage the cell. I'll explain that in just a moment, but I'm explaining how the secondary complications are due to the hyperglycemia, but the initiating event was the excessive dietary fat as the most common cause of insulin resistance. So what's the point of all this slide? You want to minimize dietary fat. Okay, it's pretty obvious, especially saturated fat, which is primarily fat from animal foods. And the other point was, this has sometimes been called the ectopic fat theory, meaning that fat is in the wrong place. Fat belongs in your fat cells, like of your belly, especially like your subcutaneous tissue. Okay? Fat does not belong, and fat, by the way, is also called adipose tissue. That's sort of the medical word for it. Fat does not belong in your liver. You don't want large amounts of fat, should not be in your skeletal muscles. You should not be accumulating fat in your pancreas. So fat's in the wrong place. There's also a type of fat that's deep in your abdomen. The way your body works is you have your skin as the external, communicates with the world. Then beneath that you have, and skin is cutaneous, so beneath something is sub. So subcutaneous tissue is where it's actually relatively healthy fat, so to speak. All fat is kind of, I don't want to say it's healthy, but it doesn't do much damage. And then deeper, you'll have fascial layers, muscle layers, and then inside your abdomen in what's called the peritoneal cavity, wrapping around your organs like your intestines, you'll have what is called visceral fat. Visceral sort of means internal organs, and that fat has more metabolic activity. That fat is more closely related to fatty liver. And fatty liver is so common, I would say the majority of adults in the United States after 45 have fatty liver. I look at a lot of abdominal CAT scans and abdominal ultrasounds, and I can tell you the majority of the patients have fatty liver. And if you send a patient in for kidney stones or something, most of the time they're going to have fatty liver. It's so common, it's not even funny. It's kind of sad and pathetic because that means they're all headed towards diabetes if they don't die of something else sooner or reverse it. Okay, let's see here. All right, I'm going to show you a little bit about mitochondria. So here is a mitochondria, and it has an outer mitochondrial membrane, which really doesn't do much, just sort of a barrier to other stuff coming in. It's typically abbreviated OMM. Then you have an inner mitochondrial membrane, which is this green lining of the inner part of the mitochondria. So the inner mitochondrial membrane is called IMM. And that's like the most important membrane in your whole body, because that's where the whole electron transport system is located, on the inner mitochondrial membrane. Then in between the OMM, outer membrane, and the IMM, inner membrane, you have this space. Here it's in red, and that is the intramembranous space. And that's where all the protons get pumped. So it's a reservoir for the inner membrane pumping protons. And that's going to be real important to know. Okay, the center of the mitochondria is called the mitochondrial matrix. And there's some very important reactions that take place in there. The most common one you're going to hear about is Krebs cycle, which is part of carbohydrate metabolism. It's also part of fat metabolism once the fat's already been broken down into 2 carbon units. Okay, Krebs cycle is also called tricarboxylic acid cycle or citric acid cycle. The mitochondria is basically the energy factory of the cell. It makes ATP. ATP is the chemical for energy in the human body. It means adenosine triphosphate, tri as in 3 phosphates. Okay. And by the way, I've got, free online lectures of all of this stuff. A lot of lectures about, carbohydrate metabolism, glycolysis, Krebs cycle, electron transport, mitochondrial function, all that stuff. The book kind of puts everything into a coherent order, and we're going to go primarily by the book, but I'm also letting you know if you want to spend a little more time with the subject, there's a lot of other lectures. There's about 1,500 lectures on this YouTube channel. Okay, glucose is a 6-carbon carbohydrate. So here's glucose. And a carbohydrate means a carbon that's hydrated. There is the carbon and then H2O. Here's H2O. This one might seem to only have 1 hydrogen, but if you sort of average it out with this one over here that has 3 hydrogen, they all end up having CHO. That's a carbohydrate, carbonless water. A fat is much more dry. The fat doesn't have any oxygens other than the carboxylic acid at the end. And what this means is, the energy comes from, breaking apart these bonds between, the carbon and the hydrogens, the carbons and the other carbons. So because this is polar, it has a charge on it with all these hydroxyl groups, there's a different electronegativity between the carbon and the oxygen. Glucose, it can be made into a polymer called glycogen, and that's stored with approximately, we can say, about 3 molecules of water for each molecule of the glycogen. And the relevance is glycogen storage is wet, it's heavy. The liver is this giant thing. It's the biggest organ in the abdomen by far. And glycogen only lasts for about a day and a half to 2 days. Whereas fat, if you just give somebody water and just water fast them, they can live about an average of 60 days. So you can store a lot more concentrated energy this way because there's no water in there. It's just the fat itself, which is super high in energy because it's less oxidized. This is already oxidized with, hydroxyl groups. OH is a hydroxyl group, also called an alcohol group. Okay, it's already half processed, if you will, half metabolized, if you will. So something that loves water is called hydro, as in water. Philic. Philic is to love. Hydro, something oily or just fat in general, is hydrophobic, water hating. It moves away from water. Okay. Now we're looking here at the first couple of reactions for glycolysis. So glycolysis is like the most important metabolic pathway in the cytoplasm, and it's pretty much the most important metabolic pathway for virtually all forms of life. It's been around for a long time. It doesn't require oxygen, so it's anaerobic, not requiring oxygen. And there's a couple key reactions in here that are worth knowing about. First of all, glucose comes into the cell. Once it comes into the cell wants to trap it. And the way the cell can trap it is by phosphorylating. So it adds a phosphate to the glucose. So the glucose becomes glucose. GLC is the abbreviation for glucose. Glucose 6-phosphate. Now that phosphate means there's a big negative charge on there and it makes it bulky, so it won't be able to exit out of the plasma membrane. It's going to stay inside the cell. Then what happens is there's another reaction called isomerase. The glucose molecule initially coming in is kind of asymmetric. It's more convenient for the second half of glycolysis to take the glucose molecule and isomerize it, means make another also 6-carbon molecule, but more symmetric, more even from side to side, so that later on in the next set of reactions it's going to be sort of chopped in half, if you will. It'll have symmetric halves that are interconvertible, and all of this means is that the second half of glycolysis is based on 3 carbon units. The first half is based on 6 carbon units, and you got to make them more symmetric with this step. Okay, once you've got them to this step, The next reaction is by the enzyme called PFK. PFK is the abbreviation for phosphofructokinase. And the reason this reaction is a big deal is it's super regulated. Glucose does not get burned unless the cell has a good reason to burn it. Burn it means, use it for energy. So if the cell is high in ATP, then it doesn't need to run the reaction. Okay, so high ATP, a little negative there, means that will inhibit the PFK reaction. High citrate, which is a metabolite at the beginning of Krebs cycle, when that is present in high amounts, it will also inhibit running this enzyme. Versus if you're high in AMP, that's adenosine mono as in one phosphate, unlike ATP, adenosine triphosphate with 3 phosphates. This means you're low in energy. So when you're low in energy, there's a positive letter right there, positive sign, and that means you want to run this reaction. So the whole point of this is that glycolysis for glucose is very, 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 very tightly regulated. Okay, the cell, glucose is the energy of life. It's like the most important energy molecule in the body. So the body is very careful on how it handles it, and the brain burns through tons and tons of glucose. The brain is the most metabolically active for glucose burning of anything in the whole body. The left ventricle is pretty close. But those are the two things. When you look at a PET scan for glucose uptake, the brain has tons of uptake, and so does the left ventricle of the heart, and nothing else is even close. Okay, it then in the second half of the cycle splits into 3 carbon molecules, and the one that's important to know about for our purpose, we're going to be talking about diabetes, is glyceraldehyde 3-phosphate. Okay, a lot of times that's abbreviated 3-PGA. So in a little bit different order, that would be 3P as in 3, the phosphate's on carbon number 3, GA, glyceraldehyde. Okay. It's a little bit useful to know it's an aldehyde, but that's more if we're going to get into the biochemistry of it. And we're not going to get into too much biochemistry, hardly any. But you still want to know this molecule. And again, usually the easier way to abbreviate is 3-PGA. Okay, and also notice that part of its name is glycer as in glycerol, okay, which means, a 3-carbon skeleton base of it, typically with hydroxyl groups on it, all right? Then it gets metabolized by this enzyme here, 3-PGA or glyceraldehyde 3-phosphate dehydrogenase. Whenever you hear dehydrogenase, you're typically going to have an NADH involved, all right? And you're going to take a hydrogen and stick it onto the NAD plus gets a hydrogen, and that's later going to be useful. It's going to function as an electron carrier. All right, but we're going to come back to this molecule, 3-phosphoglyceraldehyde, also called 3-PGA, because that gets very much affected by diabetes. The other thing that comes up out of this is that, like I said, glucose is tightly regulated, especially because of the PFK step, which is tightly controlled, whereas fructose, when fructose comes into glycolysis, it enters at the 3-carbon phase, where it bypasses the regulatory step, and that's why fructose can run through the second half so fast, because it's not regulated up front at the PFK step. Oh, this is just showing a couple more of the steps in glycolysis, and you really don't need to know these. Just be aware that the glucose is eventually processed to become pyruvate, a 3-carbon molecule, all right? And that can then undergo additional reactions that will be used to generate energy, but it's good to know it ends in pyruvate normally. Okay, so this is just another way to sort of write the same thing. Glucose comes into the cell, phosphorylated. These are the names of the enzymes called hexokinase. And the names make sense. Hexo means it interacts with a 6-carbon molecule. Kinase means it adds a phosphate. And glucose is a 6-carbon molecule, and this enzyme adds a phosphate to it. So it makes sense. Isomerase means you just take the same chemical constituents, but you rearrange them into a different form. So glucose 6-phosphate has the same chemicals as fructose 6-phosphate, but now they're arranged in a slightly different form. Their interconnections are a little bit different. Okay, and we talked about 3-PGA, undergoing reaction by 3-PGA dehydrogenase. Okay. There's 3 common inhibitors of 3-PGA, and which is 3-PGA dehydrogenase, that enzyme that processates 3-PGA, that reacts with 3-PGA. One is called PARP, and PARP is this like polyadenylyl DNA repair enzyme that really gets damaged when people start eating high-fat diets. And it's kind of a complex thing, but the bottom line is you'll damage DNA, you'll activate PARP, and PARP causes problems when somebody's eating a high-fat diet, especially with high saturated fat. Um, Alcohol also can inhibit 3-phosphoglyceraldehyde dehydrogenase. So it's pretty stupid to drink alcohol. You want to really minimize that. I recommend zero alcohol, but if you have to have a sip here and there, fine. But if you want to optimize your health and your brain, alcohol is just a toxin. Okay, arsenic will also inhibit that enzyme as well. That enzyme is important because it's sort of one of the cornerstone enzymes in diabetes that's damaged. Okay, so here I was just showing it again. Glyceraldehyde 3-phosphate dehydrogenase, the enzyme that was going to process 3-PGA, and it gets inhibited by PARP in the setting of insulin resistance, gets inhibited by alcohol, and gets inhibited by arsenate, related to arsenic. Okay, and that's why there's another one of the reasons why energy can be depleted a little bit with arsenic. Okay, once you get to pyruvate, the pyruvate can be processed in several different ways. If there's no oxygen available, the pyruvate, the end product of glycolysis, can be made into lactate. It can also be sent back through gluconeogenesis to make glucose. You can make it into an amino acid alanine. Most commonly, for our purposes, it undergoes reaction with pyruvate dehydrogenase, and it gets made into an acetyl group, 2-carbon group, and that gets sent into the matrix for further metabolism. But it could also be used, the 2-carbon groups, acetyl groups, could be used to make fatty acids. Okay, I kind of went through some biochemistry there, just so you've heard it before. You don't have to memorize any of this stuff unless you want to, but that's sort of the structural stuff. Then we'll talk about a little bit more advanced carbohydrate. And this is going to be an easy chapter. I know this sounds a little complicated, but what you need to know is not that complicated. The key thing to know is that dietary fat, especially saturated fat, causes insulin resistance, which is diabetes. Diabetes, you should think of it as being defined by insulin resistance rather than defining it as high blood glucose level. If you think of it as being insulin resistance, everything's going to make a lot more sense for you. Okay, I'm going to stop at this point and call that diabetes, 13A, chapter 13A for diabetes, and then we'll do 13B here in just a little bit.